Hello everybody and welcome to this new tutorial of OpenFOAM. Today we're gonna work on a stirred tank reactor simulation in OpenFOAM using monophase case, and we're gonna see together how to work with the Mrf approach applied on stirred tank reactor. So let's start. So this is the tutorial. This tutorial is done for two-phase stirred tank reactor, but it's okay. We're gonna work on the same geometry and also all the setup of the Mrf zone. So let's go directly to the geometry setup. So we have here, this is my folder. So I have in the constant folder, I have two surfaces, where I have an ampeller and the vessel .stl. So I have two STL files, the ampeller and the vessel. Okay, let's open these files in PowerView and see. So I'll open PowerView. Okay, apply. So this is the vessel, this is the tank. I reduce its opacity, okay, and then this is the ampeller. So you can see the ampeller and the tank, but these are in .stl format. What we need to do, we're gonna work at first with a block mesh Dict in order to generate the outer domain. Then we're gonna extract our tank from this domain and also the vessel, and then we're gonna talk about the cylinder of the Mrf approach. So let's start with the block mesh Dict. So here in the tutorial, here they are just talking about two-phase order form. This is not our case of today. And also as an information, in the version 8, I'm using the OpenFOAM version 8. And this solver is no longer available in this version. I think you can use instead two-phase mixing foam or something like this, or multi-phase order foam. So I'm not sure about the choice of the solver. Okay. And then here, so here is the Mrf approach. So what is the Mrf? So in order to consider the rotation of the ampeller within the tank, we have two approaches. The Mrf, it's multiple reference frame, or the dynamic mesh. So in the dynamic mesh, you are like rotating the ampeller and then solving for each movement of the ampeller your case. But for the Mrf approach, you are not rotating your mesh, you are considering a fixed mesh. So here the idea is to divide the domain into regions. Rotating region, okay, rotating zone, it's the zone of the ampeller, and then stationary zone. So I'm gonna show you again. So the idea of the Mrf is, instead of moving the ampeller here and calculating at each time the solution, we are just we're gonna insert a cylinder and consider that this zone is a rotating zone, and the outer domain, the rest of the tank, is a stationary zone. So this is the idea of the Mrf approach. Instead, in order to consider the movement of the ampeller, we are adding an extra term in the equation, the momentum equation. So the velocity field with respect to inertial frame and the relative velocity in the rotation zone. So this is the velocity we are using in the momentum equation instead of the absolute velocity. Okay, then here they are just talking about the setting up the simulation, but this concerns 2 phases. It's not our case. Okay, so let's start here in generating the geometry and the mesh. So at first, we gonna use the block mesh in order to generate the outer domain. So here in system, we have block mesh, and we have a cubic block. It's very simple. We just need to introduce the 8 vertices, and then assign the block with its boundaries, so all boundaries, and the top of the cube. Okay, so here we need to. So here I have 2 files, all clean to clean my case, and all run, and it includes all the commands I'm gonna execute in my case. So to start with block mesh, I'm gonna go step by step, so command by command, and I'm gonna type it in the terminal instead of run automatically all run. Okay, so block mesh. So here I have the cubic block generated. I can type OpenFOAM. Okay, apply. So this is my block. And I'm gonna open the ampler and the vessel as well in order to explain what we gonna do exactly. So here we have the outer domain, the block generated using block mesh. We have the vessel. You can see it here, it's cylindric. And then the ampler. So we're gonna use the snappy X mesh in order to cut the domain and keep only the inner domain. What is the inner domain? In our case is the tank with the ampler. And here, if you can see, so here in the boundary we are assigning the top. So this is the top in the block in the stir tank. So if we can just check top. Okay, so this will be the top in order to assign the boundary condition of the tank top. Okay, so let's go and see now the next step. So here they are talking about block mesh. The background mesh encompasses the wall surface of the vessel and mixer blade. Okay, just details. It's recommended to produce background X mesh whose edges have similar sizes to get the best results. Okay. So here they are considering the top. They are considering the top of the cube under the name of outlet. I rename it to top of the tank. So in my case, it won't be an outlet, but it's gonna be a symmetry, and I'll explain later in the boundary condition why I am considering this type of boundary. So the first batch will be automatically deleted. Okay, yes, okay. So the snappy X mesh now. Here we have, in order to keep only this geometry. So this is the idea of the snappy X mesh, is to remove the outer domain and keep only the vessel, and the ampler. Then surfaces can be visualized using PowerView. Okay. So here, if you can see, we are not considering any shaft. The axial shaft that is usually inserted in any ampler in a stirred reactor. And it's explained here, the axial shaft of the ampler system is not considered here to resolve the ampler surface with a less number of cells. Why? Because when considering the axial shaft, we're gonna need small cells in this shaft in order to keep the conversions of the solution, and this gonna engender a greater number of cells. And of course, before executing the SnappyX mesh, we need to extract the surface by using surface feature extra Dict. So here we have the surface features Dict. So this is, I think this tutorial was generated with a really old version of OpenFOAM, because in OpenFOAM 8, the version I'm using actually, they are using surface features Dict, and it is the dictionary is like this. So here, okay, so here you can see that we have ampler.stl and all these details. Instead, in the newer version, we have surfaces that we want to extract. Ampler.stl and vessel.stl, and here include the angle equal to 150. Okay, so I'll execute it now. Surface feature. So when executing the surface feature, we gonna have a file defining all the edges in ampler and the vessel, and the included angle to consider an edge is the maximum value is 150. So this will be required to generate the SnappyX mesh. To generate the mesh using SnappyX mesh. Okay, so here we have the SnappyX mesh. So we have geometry, the ampler, vessel, and here we have an extra zone which is the Mrf. So as I told you, in the Mrf approach, we need a kind of rotating zone around the ampler. It's a cylinder, here defined by searchable cylinder by 2 points and the radius, and this zone will be defined as an Mrf zone, rotating zone. Okay, and these variables, these parameters are done for the mesh generation. So here for the features, for the edges, gonna be read from the vessel.emesh that we already generated using surface features Dict. Okay, then for the refinement surface, here we define the refinement surface in the Mrf zone. The ampler and the vessel. And here this parameter location in mesh, in order to choose which mesh we gonna keep, because we will have two meshes. The outer mesh that includes the cubic generated, the cube generated using block mesh Dict, and the inner mesh of the vessel, Mrf, and the ampler. So we are choosing a point in the vessel in order to keep the inner domain and to cut and remove the outer domain of the block. Okay, so here are controls of the snap, then add in layers, and here for the mesh quality controls, instead of listing all the parameters here, we have an extra file called mesh quality Dict, and here to define the maximum value of non-orthogonality, so we are accepting 65 as maximum. Then here the skewness with boundary and internal skewness, and other parameters here. So if you are interested in refining more your mesh or improving the quality of the mesh or adding more cells, you need to review the SnappyX mesh and also the parameters mentioned here in mesh quality Dict. Okay, so now I'll run SnappyX mesh override just to overwrite the old mesh created with block mesh Dict. So the option override is to keep the newer mesh of SnappyX mesh after each iteration. Okay, so the SnappyX mesh is done right now. We can run Mrf. Okay, so here so here you can see that our mesh is ready. So this is the vessel, this is the ampeller here, and the top, we can see here the top, the vessel wall, and the ampeller inside. Okay, so now that our mesh is ready, let's go and see the boundary conditions of velocity, pressure, and turbulence. So for the velocity, the common error is to assign a rotating wall of the ampeller, and this is not true, because in the Mrf approach we need to assign that our ampeller type fixed value 0, 0, 0. Okay, because the rotation of the ampeller will be defined in a separate file called Mrf Properties and located in constant. Okay, so here we have the top. So this top, in the tutorial they are calling it an outlet because it's an outlet for them, but in my case I'm gonna consider it a symmetry. Why do I consider this boundary as a symmetry? It's like continuity of my domain. What is happening here, if you get a bigger domain, the same thing gonna be happening here in this side. So this is the idea of symmetry. Okay, so top symmetry, the vessel 0 and the ampeller absolutely 0. So here then the pressure and the turbulence, I define the function at the wall in the near the vessel and the ampeller, also for K and epsilon. So the top is symmetry, and vessel and ampeller I used wall function. Okay, so now we have constant. So in the constant folder I have the Mrf properties, and in this file we can check here in the polymesh boundary cell zones we have the cell Mrf zone already defined in this file. If we don't define the Mrf zone, we won't have this file filled in this way with cell Mrf zone. Okay, so our Mrf zone is already defined. So now we gonna go and see the Mrf properties. So here we have Mrf Ampler, its name. Then cell zone, we're gonna choose the cell zone name, which is cell Mrf zone. Active, yes. And then, for example, if this zone includes extra patches, in our case we have only the Ampler and it's rotating. For example, if you have extra patches included in this zone, but you want to define, for example, that this part is not rotating, just you need to include the patch name here to say that this patch is not rotating. And then the origin of the rotation and the axis, we are gonna have rotation around the y-axis. And for the omega here, it's radian per second, so it's the equivalent of 120 round per minute. Okay, so for the momentum transporter, it's the turbulence model. We choose K epsilon. And here we have the standard FV schemes, FV solutions, and okay, here we don't have omega, we can delete it, but it's a common file in the tutorials, so it doesn't impact our simulation. And here are the schemes and control Dict. I'm using OpenFOAM. This is really very basic case just to let you know about the Mrf approach and how it is done. And if you have more complicated things, for example, two-phase or multi-phase using stirred reactor, the Mrf approach is the same. You just need to adapt the, for example, here the name of the solver, the files, just the way it's done in this tutorial. Okay, so now our case is ready. We can run OpenFOAM. Okay, because here I have 0.original and I'll copy it to 0. Okay, OpenFOAM, and here it is. So now that is ready, I run the simulation for 1000 steps. So I run perform to see the results. Okay, apply the velocity. Okay, so this is the velocity. I'll do slice. So here you can see that we have a kind of circle here, and here we don't have. Okay, let's see together. So here we don't have a shaft, rotating shaft. So here it's like a dead zone. So what is really mixed is in this zone. And here we have the wall, so the velocity is equal to 0 in this part. So we can see that here we may have vortices as well, because the fluid does not hit any baffle. We don't have baffles here in the tank. So we have this type of behavior of the fluid within the mixing system. So we can do slice to see inside. Apply. and here it is the slice. Okay, I'll color it. Okay. So you can see here that this zone and this zone are mixed. So we have velocity here, but this zone in this part of the tank, we have velocity near to 0. So this is not very homogeneous for mixing two-phase, for example, if we are interested in the homogenization of liquid solids or something like this. So this is not very optimal. So the idea is to, for example, insert here. Okay, apply. So insert here, here, and here buffers in order to block the fluid and to create turbulence, more turbulence within the tank, and to avoid this type of vortices. So here we can choose stream tracer on the Y direction, then here apply. So you can see here how the fluid is rotating around the axis of the tank. And this is not good when the objective of the mixing is the homogenization. So this is all for this video. Thank you for watching and see you in next tutorial.